So we talked about sparse linear models or sparse linear regression and covariance estimation and structured covariance estimation. I want to talk a little bit about, so there are different things that we can talk about from here on. So we have sort of talked about the basic building blocks of, I would say, high-dimensional statistics. There are various topics, some of which you guys can talk about, hopefully. What I think is useful to do is to talk about non-parametric regression, because as we'll see, there are some techniques that are used here that are very useful. So that's what I'm going to do a little bit, talk about non-parametric regression, and we'll see whether we have time to talk about anything else. So do people know about non-parametric regression? What is non-parametric regression? Any idea? Yeah.
Usually it's like allow like your prediction of like expectation of like y and then x like some over some future class.
Right. Okay. So yeah, a very general way of modeling things is like I have x and y, right? It's like the machine learning approach to learning or estimation. So you want to predict y based on x. And one thing that you can do, you can try to learn the entire distribution, joint distribution based on IID samples. So this is the setting that we take, for example, in statistical learning theory. And like a more modest, let's say, goal is to try to just estimate the conditional expectation of y given x, right? So if I'm given a training set, IID sample from this distribution, I can try to estimate this. In linear regression, you assume that this, for example, is like beta transpose x, so it's a linear function. In non-parametric regression, you assume that this belongs to some function class, as Kyle pointed out. Generally, you don't want to like impose any constraints on this. And in fact, if you have taken 231C with me this quarter, you can estimate this with very mild assumptions on it. So basically, as long as this exists, you can estimate it consistently. It's called universal consistency. But there's not much else beyond that you can say. You can't say, for example, how fast I would converge as my sample size grow. So for example, you could do KNN. So you can do K nearest neighbors. That's a universal estimator. You could do partitioning estimators. You can partition your space X into pieces, and you can average values of Y over each piece. That's another sort of universal estimator. But in order to say something about how fast you can read, it could be very slow. So if the function, this function is very complicated, it could take a lot of samples to get close. So what you usually assume, so this is the simplest assumption. That the traditional assumption is assume it to be just a linear function. This is quite easy to estimate. We saw that even this is not as easy as it might seem if x is high dimensional. So if the dimension of this x is very large relative to the sample size that we get, so the samples that we get are x1, y1 up to xn, yn. But we had sort of ideas how to get around the high dimensionality by assuming that like beta is a sparse, for example, there are just some of the features that are active. So in non-parametric regression, this is more traditional. So you'd assume that this is just some function, but you're not going to assume that it's, so this is called parametric model because the function is parameterized by these betas. Non-parametric regression model, there is no parametric form. Usually you just assume that this belongs to some function class. For example, you can assume that f is the set of all functions x from, let's say, rd to r, such that f is one Lipschitz. Okay, so this is some structure. It's not totally arbitrary. So this requires some smoothness. So things are continuous, and the derivative exists. The derivative cannot change as fast as you like. And this is a form of smoothness. You can assume higher order smoothness. For example, you can assume that f prime is one Lipschitz, or like so f is 1 Lipschitz means that the derivative is bounded by 1. You can assume that the second derivative is bounded by 1. The first and second derivatives are bounded by 1, or the first and the second and third are bounded by something. As long as you assume higher order derivatives are bounded, the function becomes more smoother. So, so in this setting, usually smoothness is what replaces disparity. So the function class, this function class is big. You've seen, so if you recall the metric entropy calculations, the metric entropy of this class is bigger than any finite dimensional metric entropy. So we did it for the ball of radius d, for example, and we saw that so L2 ball in d-dimensional space, the metric entropy is d log 1 over epsilon. This guy, the metric entropy is like 1 over epsilon. So it's like exponential in 1 over epsilon. The covering number is exponential in 1 over epsilon. But still, the question is that suppose I have a sample size n, I have this sort of smooth assumption, can I recover anything? Okay, that's the idea of non-parametric regression. I can't sort of write a parametric form for functions of this form. Okay, so there's no easy way to express f as, for example, so one simple thing to do is like assume, let's say, for example, if f is a Hilbert space, what you can do is that you can assume that there is a basis, and I can write f as a linear combination of these basis functions. So this is a basis for, so let's say it's a Hilbert space S, this is the basis for H, then it would look like a parametric model. So every f in the Hilbert space I can write as, so this is not the Hilbert space, but if f, so if, let's do this, if f belongs to H, where H is a Hilbert space, it's an infinite dimensional basically Euclidean space. Then f can be written usually like this, where phi I from 1 to infinity is a basis for H, and these betas are in R. And so this looks like this. It's not exactly this. It's just that we have a bunch of parameters that now we can try to estimate. So these are the functions, right? But still, the parameters, the set of parameters is infinite, or the number. Sorry, the number is there's like at least uncountable, not uncountable, countably many parameters, so infinitely many parameters. So this differentiates the situation from traditional linear models. And this situation is even worse because we don't even have this basis to estimate the coefficients over that basis, basically. Okay, sounds good. So that's the setting. Okay, so there's one more piece, which is, I'm not going to emphasize here, but it's worth remembering that what we can in general do is I can always assume that this is some f, and then I can write y as y minus, or sorry, let's say f, let's call this f star. This is the true f, plus y minus f star x, right? This is always true. And then I can call this some v, okay? The issue is that this, in general, actually have to do this, the random x. And so I condition on x. So f star x is basically expectation of y given x. Now this is a random function. It's a deterministic function, but evaluated as random x. And then I have this. So now this is a new random variable, which I'm going to call noise. The thing is, this is in general dependent on x itself. In the traditional like literature, usually what you'd see is that you'd also assume that this is independent of the noise. Sorry, independent of x. So this is independent of x. So an assumption is that v is independent of x. Then the model would be like some sort of an additive model. You have f star x plus some independent noise, and then you draw IID samples from, because it doesn't depend on x, this is going to have a single, like a certain variance, for example, and so all of these would have a noise that have the same variance. So this is called homoskedasticity or homoskedas. Yeah, I can't pronounce that, but the noise has the same variance in general because this depends on x. The variance of v would be just the conditional variance of y given x. And so the conditional variance could depend on x. So in the more general setting, there is this noise here, but depends on x. The variance could depend on x. When you sample these, you're evaluating this at different x's, and so the noise variance could change. So the noise would be independent for these training data, but the variance could change in each iteration. So some of the classical results work for this general setting, but for the most part, I'm going to assume that this is independent of x, so you can model this as some sort of a independent noise. And often, what you're going to do is that you're going to sort of simplify further, assume that this is just some Gaussian noise. So this is a very simplified, I'm going to put sigma here, W, where W is like normal 0, 1. This is the most simple assumption. So this V is just Gaussian, and then this is going to always have conditional 0 mean, right? So expectation of V given X is going to be 0 because we subtracted the, so this is always going to have 0 mean. So I should have mentioned that. So expectation of V given X is 0 by the construction that we did. So this means that the expectation of V is always 0 by the iterated expectation or smoothing. But the variance could depend on X. What I'm going to assume is that the variance does not depend on X. So, and this is further like a huge assumption that the noise is actually Gaussian. But once you do these simplifications, this is the model that we usually work with. Okay, so you have y is f star x plus sigma w, and then I can condition on x. This is going to be independent of x. You can treat x as deterministic, so we a deterministic design setting. The only randomness is because of this noise. So I get yi's are random because of, what I get is some sort of a model like this. Yi is f star xi plus vi. This is for us usually sigma wi. These are usually assumed to be deterministic, and wi's are usually assumed to be Gaussian. So that's the setting that I usually end up with. Okay, sort of clear. But just know that some of the results extend to this more general setting. So you don't have to assume the Gaussianity here. For example, a lot of things that we talk about sort of extend to if this is sub-Gaussian. But the key here is the more serious assumption is that the variance of this does not change with x, or basically it's independent of x, which I would say is a more serious assumption. Okay. Questions? Okay, so what you can do here is, what are some natural things that you can do? You can try to, in this additive model, you get yi, and you know, for example, in the linear case, you can solve least squares here. You can also solve least squares. You can try to find a function whose values at xi's are close to yi, right? By minimizing this. And I'm going to minimize this order class f, which I'm assuming that f belongs to, for example, class of all Lipschitz functions. So this is a value estimator. And I can also, if this class has some norm, so for example, if this is a Hilbert space, there is some sort of a Hilbert norm, I might instead or in addition, so assume that f is an f and also can regularize by the norm. So if the norm, for example, I'm not going to talk about this, but if you know what an RKHS is, these are a special kind of Hilbert function, like Hilbert spaces of functions. The norm usually measures good properties. So for example, it might measure smooth or roughness, the opposite of smoothness. So if I penalize by the norm, I'm penalizing by the roughness of F. I'm going to give some examples, what it looks like. But these are the traditional kind of things that you might want to do. Whether you can actually solve these problems in their generality, it's a different question. From a statistical perspective, you can consider the estimators. In practice, they're often infinite dimensional problems because you have to optimize over a class of functions. It may or may not be possible to even approximate the solution, but that's something that we don't worry too much about here. So what we worry here is whether these estimators are good or how good they can get, okay? How to compute them is left to some other, let's say, course. I'm going to talk about an example over in RKHS, for example. You can solve this rather easily, actually, but the general setting is different. So any question? Okay, so linear regression is a very simple example. So if you think of the setting with function classes, if I take my function class to be the sort of all functions that look like this, okay, beta x, and beta is in some c. I'm going to call this f in c, let's say. This is one function class, right? So I can assume, for example, the c is a set of all S sparse betas. That would define a function class, and this, for example, if that's the case, if I'm looking at S sparse linear functions, solving this would be equivalent to solving this would be like the L0 penalized regression, or solving this would be finding the best sparse linear regression fit, for example. And then if you write, so the function is there, so if you write it, it's just the usual least squares criteria here. And effectively, you're estimating, like minimizing over this class of beta, and that's just like a restricted or constrained least squares regression problem. Sounds good. So nothing new here. So for example, if you take the C to be the class of all betas such that the L2 norm is controlled, that's a constrained ridge regression problem. You can take it to be the LQ, you can take it to be like the L1, you can take it to be L0, and so on and so forth. So the L1 corresponds to, for example, constraint, let's so and so on. But a more interesting case is, for example, consider the class of all functions for which the second derivative exists almost everywhere and is in L2. So this is a kind of a Sabolif space. So Sabolif spaces are spaces for which the function and or its derivative are in LP. So L2 norm for a function is, so if you have a function g, let's say, from 0, 1 to r, you may know that the L2 norm is just, let's say, the L2 with respect to the Lebesgue measure. The L2 requires a measure on the underlying space. So let's say L2 with respect to the Lebesgue measure is just g, let's say x squared dx square root. And so, okay, so the squared. So the L2 squared is something like this. And what this class is imposing is that the f double prime, the second derivative, for example, or you can say the first derivative if you want, is an L2. So if you work with this class has to be sort of smooth because the fact that this is finite prevents f from varying too much. Okay, so if this the first and the second derivative tries to like oscillates a lot, So if you have a function that just does this, and you try to take the derivative, things add up, and so this could blow up. So if you restrict this, you rule out some of these, you can say rougher functions. You get a smoother function. So something like this might be in that class, but at some point something like this might be out. And then there are functions for which this is infinite, no matter what R you take. It's not going to there. So if it's the case, we can try to minimize this least squares over this class of functions, and you can penalize by this norm squared, because this sort of measures the roughness. I can add it there. So the minimizer of this problem, this is called the cubic spline. And it turns out to be piecewise cubic between these design points. And the second derivative is continuous, third derivative has jump discontinued the knots. This is an example of a kernel ridge regression. And this is an example of this RKHS setting. You can actually reduce this to a finite dimensional problem using the theory of RKHSs. And so this is an example, for example, you can actually solve. You don't have to. So the solution optimizing over this infinite dimensional class reduces to optimizing over a certain finite dimensional class is just defined by these knots. And then you can actually write down the solution. Okay, so you can solve a linear equation and write down a closed form solution for this. Okay, so this is an example which is rather outside this type of setting that we have discussed. Okay, sounds good. There are other things that you can do here. So you could do the total variation denoising. There's another thing which is you put an L1 on the derivative sort of. That turns to find the piecewise constant functions and so on. I'm going to skip this so you can translate it to the kernel ridge regression. There's a chapter in the book talking about the kernel regression. And so you can write this as some sort of a problem like this over Hilbert space, where this penalty looks like the Hilbert norm, and then you can actually reduce it to a finite dimensional problem. Okay, let's give that. Any questions so far? So that's the setting. Okay, so what I'm going to do now is I would like to jump a bit ahead. Instead of, I'm going to tell you how this is related to the non-parametric regression, but there is a much simpler model, which is the prototypical example of these non-parametric models. And it turns out that studying these this model is very useful. So this model is this very simple model where you have observations yi. There is some theta star I, which is the mean of this, plus some noise, which is zero mean, and there's variance sigma. That's variance sigma squared. So you can compactly write this as a vector y and then vector theta plus sigma times w1, w2, wn, where SW is normal, which means 0 and identity covariance matrix. So this would turn into a very simple vector equation like this. Okay, so everything is in RD. So all of these are in Rn. Sample size is n. Okay, so does this model remind people of anything that you've seen maybe in 200B? Have you seen this model before? Does this remind you of anything? Sorry, what was that? Stanford Johnston? Johnston. Oh, okay. Okay, so okay, Ian Johnston.
Yeah.
Okay, so it's interesting. So this model is related to this guy. Okay, it's true. So he has written a book on normal means models. Yes? You can calculate the maximum likelihood here because it's Gaussian. So if I give you y, you can actually calculate the maximum likelihood estimator of this. So what is the maximum likelihood estimator actually? If you try to do maximum likelihood, what would it be? So the likelihood would be, let's say sigma is known and is 1 for simplicity. So the likelihood would be, so y is theta plus w. So this would be normal between theta and covariance identity. So this is going to be proportional to e to the negative 1/2 theta minus y, or y minus theta squared. All the theta is different. Okay, so what was the conclusion?
The observation.
Right, so if you do max argmax fy given theta, if theta is in Rd, Rn, then this would be like, so that's the MLE. So that would be just y, right? So the best estimate of the ith coordinate that you have is just the ith observation. Like intuitively, it's clear because all these thetas are different. This guy doesn't have anything to do with this if you don't have any constraint on theta. So if you do the unconstrained assumption, like there's no assumption on the theta stars, the maximum likelihood would be y. Okay, so was there anything else that you wanted to add here? This is a good estimator, bad estimator. Okay, so that's the, yeah, James Stein. There's another name associated. Two names, so James and Stein. So what these guys show, so Ann Johnston has like written a book, Normal Means Model. It's supposed to come out, like, I don't know if it has come out or not, but it's there. So there's a book on normal means models, and probably can find it on his website. There is the there's the James Stein phenomena that these guys showed that this can be beaten like uniformly. So this is inadmissible if you think of the quadratic loss. So there is another estimator. If you think of minimizing or measuring the loss, so I have theta hat minus theta star. This can be beaten by another estimator. So this is going to be, sorry, strictly bigger than another estimator, which we call James Stein estimator. So you can refer to the homework problem in 200B. So this guy shrinks towards 0, and in D bigger than or equal 3 or bigger than 3, I forgot, something like that. The loss of this in the aggregate quadratic norm is strictly better than the MLE. So this is an example of a high-dimensional phenomenon. If you want to do aggregate estimate, sort of you can borrow information from the other ones, although they don't seem to be related. It turns out that because of the structure of the loss, because you don't care about the individual estimation, you care about estimating in the aggregate. So this is the sum of all errors over all the elements. You can beat this guy. So there's a non-trivial estimator that sort of shrinks. It does something like 1 minus, I forgot the constants, but there is something down here that's something like n minus 2, I don't know, plus times y. I forgot the exact thing, but you shrink towards 0 when y is small. So when this guy is small, you make it smaller, and this beats it. Okay, so this is not the classical. So the classical statistics, in the classical statistics setting, this would, all the theta stars would be the same. So there would be one parameter that you observe, and you observe it like entire sample size n. So all of these would be the same. Then you could do much better. So I can take, for example, the average. When I take the average of these would be the same parameter, but the average of this would have a much smaller variance. So I can reduce the variance. That would be the MLE in that case, and so that's how you can actually estimate. But this model is sort of the prototypical example high dimensional model. If you observe a vector whose dimension is growing with the number of observations. So there's no way that I can sort of improve by increasing this if I don't impose any constraints on theta star. So the point here is that, so this is an interesting phenomenon, but we want to actually do good estimation. What we are going to do is we're going to impose a structure on theta star. Because theta star is not anything in Rn, but it's in some subset theta, which is well behaved. And so you can see, for example, that those models that I mentioned can be reduced to this model in various ways. There are various ways of reducing them. And in every case, this theta star turns out to be in some structured subset of Rn, not Rd, Rn. And so we can actually do better than the MLE. So a natural thing would be to, in that case, replace this with, so do argmax, for example, theta in theta, rather than that, and that oftentimes produces good estimators. And this, in this case, would be like argmin y minus theta squared. If I try to maximize this, it would be minimize over. So this is like find the theta that's closest to y, but it's in this theta, capital theta. So this is an example of a sort of a projection estimator. An example. Okay, so for now, accept that this non-parametric regression model reduces to this. Let's study this. I'm going to come back and tell you how we actually can connect it to the non-parametric model. Okay, so the point is that we're going to reduce the non-parametric model to this normal means model, but the effect of, for example, smoothness and other like structures that we put on the function appears as theta star, this vector being in some specific subset of Rn. Then by imposing assumptions on theta or there, we can get like assumptions here, and then we might do better by just projecting onto, instead of trying to minimize over all theta, which gives me y, I'm going to minimize over this, which gives me some non-trivial solution. Sounds good? Okay, so we're going to come back and connect this in order to avoid repeating myself. I'm going to come back later and do that. Any questions, comments? Okay, so now what I want to do is try to understand this projection estimator. Okay, so we want to sort of, can we say anything about something like expectation of theta hat minus theta star, where theta hat is, so this was the unrestricted MLE, say unrestricted MLE. This is the restricted one. I don't know if I have any notation for this. Yeah, I don't have any. Okay, so what can we say about how well, for example, how fast does this go? Like, how fast does it go to 0? 0 as a function of n. So you can see the sample size and the dimension of the problem, like the parameter, is the same in this model. Yeah, so there's no there's no d and n, both are the same. The only thing that helps us is the structure that we put here. So it turns out that there's a nice connection between how well you can estimate how fast this goes to 0, whether it goes to 0 at all, and the geometry of theta. So there are geometric properties of theta that appear in the solution. That's what I would like to talk about. So in order to do that, we're going to need some notation here. So the notation is for any set theta subset. So now I'm switching to RD. Later on, we'll switch back. So call this D or N. This is, I'm going to call this D because my notes are in D, but you can think of them as N. There's no, the D and N are the same, let's say. So theta is some subset of RD. Let this be the intersection of theta with a ball of radius u centered at 0. So if I have my theta here, say this is theta, what I'm going to do, let's do this, something like that. Say theta is this. Okay, fancy. I'm going to put a ball of radius u around the origin. And so this part, which is in the intersection, that's theta u. It's like a neighborhood of radius u around 0 in theta. And in fact, what I want is that I wanted to do this at a generic point. So I'm going to translate to theta naught. That's sort of going to be our, let's say, true theta. So we have theta, this notation, theta sub theta naught is theta minus theta naught. And this is just the set of all, this is the set of all theta in, set of all things that look like this, theta minus theta naught, where theta belongs to theta. Okay, so if I have basically something like this, and this is this is theta naught, that's my set. After translation, I would get this is going to theta naught is going to come to 0. So I'm going to map basically. I'm mapping theta naught to 0 here. Okay, so this would be, if this is theta, this would be theta minus theta naught. So the point of interest would be shifted, like moved to the origin. We center things at theta naught. So then I'm going to take the intersection with a ball. So now what I'm doing is effectively looking at the neighborhood here. Right. So what you can think of this doing is effectively I'm doing like a neighborhood of size or like radius u around point theta naught. But I'm shifting everything to the origin because that would be simpler. So this is the notation. So it's a neighborhood of radius u around theta naught. Okay. It's a lot of notation for something which is quite nice, but that's the meaning. Okay. Meaning of the notation we use. The next thing is to try to measure how big this is, how big this set is. And one thing that we can do is that we can use metric entropy ideas. The other thing that I mentioned when we talked about is to use random processes to measure bigness, and that's what we're going to do here. Because remember, we have a Gaussian here, and so it's natural actually to use a Gaussian vector to measure how big a set is. And this is the notation that we're going to use, or sorry, the notion that we're going to use. So in order to measure the size of a set T in RD, we're going to look at this quantity, which is the supremum of, this W is random Gaussian vector in RD with identity covariance matrix. So we're looking at basically the supremum of a Gaussian, if you want the supremum of a Gaussian process. So theta maps to, this is a process, if you think of this as defining process. W theta, then the expectation of the supremum of x theta, theta is this quantity. And we have seen things like this before. Even if you don't think of this as a process, this is a well-defined quantity. Why this is useful as a measure of complexity. This is called the Gaussian complexity. Let me tell you about something else which is very much related, this is easier to justify. There's this thing, which is called the Gaussian width, without the absolute value here. And this you can show that this is actually equal to 1/2 expectation sup W theta minus theta prime, theta and theta prime in T. Okay, so this can be related to this. It's very close. So for example, T is symmetric. Around 0, these two are the same. Because I can flip, just argue that if T is symmetric, they're the same. And this is equal to this always, whether T is symmetric or not. And it's not hard to justify this for yourself. And this is measuring a sort of a width of a set in direction W. So if you think of a, suppose I have a set, like a strange set. Yeah, so let's say this is my, I have this weird set. Okay, what I'm trying to do is I'm trying to measure, so this quantity turns out to be actually invariant to shift. So what this is doing is that if I take W, so you take direction W, this is a Gaussian direction, it's random, but let's say I realize one example, then W in the inner product with theta, it's this function whose level sets are like this, right? So they're orthogonal to this line. And so what happens is that when I try to compute this, I'm gonna move it until I hit this part, and I'm gonna move it until I hit that part. So the largest in this direction, that would be theta. The smallest would be this point, would be theta prime. And the largest in this direction would be this width. It's not hard to argue that the supremum, if you fix W, the supremum of this linear function, basically theta minus theta, this supremum is the width between the last time I hit on this side and the last time I hit on this side. So you move it. If I move it here, there's no theta here. So this is the smallest that this can get. So this is like, if you want, it's supremum over W theta in T minus infimum W theta prime in T. This is the smallest that you can get. So you have to move this. The level sets are sort of indexed by the value of the function. So if I move it in this direction, the value, it decreases. So I'm going to decrease it until I hit this. There's no more point to go. So that gives me the infimum. If I move it in this direction, I get the hit this. That would give me the supremum. And the difference is just, you can geometrically see it's the width in that direction. So half of this is like a radius, okay, in that direction. And what this is doing is that this is going to change randomly W and then measure this and then takes the average. So it's like a average width of the set. So it's a very nice, like an aggregate measure of how big the set is in various directions. Okay, so if it's like, the set is something like this. So if you look at the diameter is very big. The diameter is the worst case. So it's like the supremum difference, like theta minus theta prime. Theta and theta prime are in theta. So the diameter of this is this big, but the Gaussian width would be very small. Why the Gaussian width would be small, much smaller than the diameter? Yeah, so for example, if you take W in this direction, the width in this direction is very small. The width in this direction would be like, so actually it's not going to be that. But the thing is, the worst case, which is this, happens in a very specific direction, and that's not, so you're going to take the average between this and the case that you have this, for example. it's not going to be too small, but it's going to be smaller than the diameter. Because in one direction, it's this worst case, but in other direction, for example, if you, the best case is if W is in this direction, the width would be this, half this would be the, like the thing that you see here. If you take it to be like something like that, I don't know, the worst case would be, so that would be the width, for example, in this direction. So it's like gradually changes. It's not just the worst case, it just transfers between the small value and the large value, and then you take the average. So the Gaussian width would be smaller. So it's a much nicer stochastic measure of the size of the set than the worst case. So for example, you can compute it for the L2 ball. For the L2 ball, what do you guess the Gaussian weight would be if you try to? So if I have, let's say in R2, what would the Gaussian width using these sort of ideas? So the width in every direction would be the same, right? And like would be half this but then you have to average. That's the averaging going on. So the average would be what? The average would be the same, right? So what is this? What is this width, basically? Yeah. The image of the Gaussian? What do you mean by the image? So this would be like expectation. Yeah. Yeah. The Supremum would be 2, right? In this case, it would be 2. No? It's actually that, yeah. Is it? Right, okay, so that's the, okay, so, right. Yeah, so, right, okay, so yeah, this was not, yeah, so, okay. This is not exactly the,
It's going to be the expected value of the projection of W over
let's do this. You're right, there is some sort of a, so what is the Supremum? Let's do like analytically. So what is the Supremum over this ball? The what? W is like a vector. Would be the norm. The norm 2 of W, right? And not the square, no. So that's like the Cauchy-Schwarz. So W, this absolute value actually. Right, so this is going to be 1 for us because we're on the ball. So that's going to be bounded, and it's actually equal to that. And this is bounded by what? Sorry? The square would be chi-square. This is going to be like root expectation of this square. Yeah, it would be root d. At most would be root d. Right. If you wanted to like to be the exact weight, you have to divide it by the norm of W. That would measure the. Yeah, there's the size of this that you have to take into account. So that would be root d for the ball, for example, L1 ball. L1 ball looks like this. in R2, it looks like this. In high dimensional space, it's so what would it be for the L1? It wouldn't, no. So what is the supremum if I take the supremum over the L1 ball? Like the whole layer is inequality, right? What is the dual of the L1? L infinity. So this would be the expectation. You're going to verify that this is going to be L infinity. So what is the expectation of the L infinity? This is like expectation max over I Wi. Yeah, so this is something that I hope you remember from this course. This is bounded by root, actually I guess 2 root log d. Check the constant here, but something like this. It would be of the order root log d, right? The maximum when these are sub-Gaussians. So root 2 log d. So you can see this has a much smaller width than this guy. So this grows like root d. This is a much smaller set in the d-dimensional space. That's sort of, again, one of the things that allows you to, one of the things that Lesso sort of leverages, that this set is much smaller than what you expect. It's hard to visualize what this is called cross polytope, the unit ball, the L1 ball. It's called the cross polytope, and it's much smaller so you can see there are directions in which the width is like 2. Here the width is 2, but the directions in which the width is smaller. So in this direction, for example, right, things are smaller in a sense, right? So they're like average, things would average out. The average width is much smaller. Okay, sounds good. And then once you understand this, this is something close. So, sorry? What does this mean? So it means that this is a much smaller set on average. If you look at different directions from the so as I mentioned, this is measuring sort of a width in direction W. So this is saying on average the width of this is much smaller than the width of this. Okay. Harder? It's smaller set. Smaller usually means better in a sense, right? So when things are smaller, you expect things to be easier to estimate. The thing is that this is like inscribed inside this. Like there are some points that they touch, right? They touch at the unit basis vectors, but like in 2 dimensions, they don't seem much different. There's like a little slight, so you can see in this direction, the width is slightly smaller, right? Then the worst case is this direction. They have the same width as the L2. But in high dimensions, there are a lot of like, this point is much closer to the origin than for example, this point. This point is like at distance 1, this point would be, it's like 1 over n, or 1 over d, 1 over d, 1 over d. And so the distance is, what is the distance actually? So it's like 1 over d. So what is that? The distance at that point. Is it 1 over root d? Is that? So the point that's here is, sorry, has has all the coordinates being the same, right? So the point 1d, that's, what is the L2 norm of this? Would be root 1 over d squared d times, right? Is this correct? This is 1 over root d. So in this direction, the distance, like the width is much smaller, like twice that. But in that direction, it's 1. So you're averaging over things. The average would turn out to be this. Yeah, this might not be that. Yeah. Not sure if the geometry is correct too. So you want to measure between the two faces. I'm not sure if that's going to be 2 over repeat, but try to visualize yourself. This might not necessarily, but there are points here that are closer to, or this is like on the L1 ball. This is on the L1 ball, but the distance to the origin is much smaller. Questions? So, okay, so this was the geometric idea. So this was just a detour basically. So we need this quantity. So how can we use this? This is the complexity relative to the width. We have just this absolute values here. As I mentioned, if you don't have, if t is symmetric, they're the same. This is a better measure. So the width is a better measure of size because you can show easily that if you shift this to a point, this doesn't change. So it's actually really shift invariant. This is not shift invariant. So the origin matters here. So that's that. But we're gonna do like properly apply it. You're not gonna, we're gonna apply it locally to the place that we want. So, so the result is something like this. So if I look at this projection estimator, then we have this nice general result that if the y is generated from the normal means model, which means that y is theta star plus w. W is normal, which means 0 variance sigma squared ID. And in this case, I'm choosing D here. And if you look at this projection estimator, and if theta star, so this is theta shifted to, so that theta star is at the origin. So we shift the origin, like the coordinate axis, so that the origin is on theta star. If this is a star shaped, which we come back to, that's the assumption that we make. Then this projection estimator theta hat satisfies this bound. And the key quantity here is this GUT, which is related to the Gaussian complexity. So that's the Gaussian complexity. So what is it saying is gamma theta star. U is just supremum theta. W or theta is in theta star U. If you unpack this, this is just saying expectation, supremum, let's say theta minus theta star. Sorry, it will be like theta star plus U, I don't know, times theta, where theta is in theta, something like this. But it's easier to look at it like that. Is that, no, sorry. Still not good. Just remind you what this is. You can unpack it yourself. So theta star U is theta star intersect the ball of radius U. Right? So this is the sort of all theta minus theta star such that theta belongs to theta, and then we need theta minus theta star to be less than or equal to U. That's sort of the set. So it's all the things that look like this, and the norm is bounded by U. Theta minus theta star. Okay, that's the result. So the thing is that the Gaussian width of this local geometry. So this is a unit, like a ball of radius u, centered at theta star. What part of like theta we carve out? That's sort of this thing. So I put a ball of radius u around theta naught. This is the piece that maybe I should do it here. So there's like this thing here. Let's say this is theta star. I put a ball of radius u, and this is the area that that's the set of interest. That's sort of theta. If this is u, this is this direction, like this radius is u, then this would be theta star, theta star. And so how big this is as a function of u, basically, as you vary u. So you start with some small radius and you increase it, how big this grows as a function of u appears in the bound. Okay. So it depends on the local geometry of the set around the true parameter. The t here is just by these concentration results gives you some juice here to use, but the main object is this guy. Okay, so that's the result that we had. So what do we mean by a star shape? Anyone knows what star shape means? Can you say that again? Sorry. Yeah. You go ahead.
If you multiply it by some constant, it will still
Multiply by a constant. So let's say t is star shaped.
have some element.
So you're saying if t is in t, then alpha t is in t. As long as alpha is in 0. Yeah, so the idea is if you have a set, this is star shape, for example. So for any point here, if I connect it to the origin, anything in between is in there. Anything outside need not be in there. So if everything is there, that would be like a cone, right? So if this holds t is in t, then alpha t is in t, that's a cone. Star shape is weaker assumption. So you're saying whenever I have a point there and I connect it to the origin, anything between that point and the origin is there. It's like that. And in some direction, there might be nothing. So basically, so it need not be convex, for example. It's a very mild assumption. Anything between any point and the origin has to be. And then the way that we assume it, it's this guy is a star shape with respect to the origin. Effectively, it means that theta is a star shape with respect to theta star. Okay, so relative to this theta star, the way I've been drawing these are star shapes. So anything is there. This is not a convex set, but it's still star shape. Okay. Yeah. What are some other stars? Yeah. So something like basically a bunch of lines like this go out of the. It's also star shape. Right. So it's basically a union of these things, basically. Okay. Questions, comments? So I'm going to come back and prove this, but this is a fairly general result. You can see there is a mild assumption on this space, but then you can relate the geometry of the space and how fast, how big the set, how fast the set gets big locally to how good your estimator behaves. So I just want to explore the implications of this result later on and come back and prove it. So the first thing to do is whenever you have a bound like this, I have a bunch of parameters that I can choose. So t is not that important. This u is important. One thing that we can do, we can optimize over this u, and you can see it's not hard to argue that one of them goes down, one of them goes up as I change u. So one thing that you can do is, so this one goes up because this is measuring the complexity, the width. And you can imagine the size goes bigger, this gets bigger, but this is going to grow slower than u, it turns out. So this gets bigger faster, so this goes down. So this goes down as I increase u, this goes up. So I'm going to try to balance. You can try to optimize. And it turns out that the best choice is just to set the two equal. So the u that sets them equal gives you the smallest possible solution. So what you end up doing is you end up with this sort of sorry, let's see. So yeah, like imagine. So if I set these equal, so 2 sigma g u, I'm going to ignore the t. So let's say 0. 0 is bad, but okay. So let me set it equal. So set this equal to root 2 sigma g u t. What I get is, what do I get? I can cancel one of these. So cancel one of these with that. So I get 2 sigma g u t over u is equal to 1. Or I get 2 sigma g u t equal u squared. Okay, so the u that works is u squared is equal to, so I have to solve this equation that would give me a good u. And if you ignore this part, basically what you're doing is you're basically saying gut is equal u squared over 2 sigma. Or basically Gaussian, ignore this part, the Gaussian weight has to be equal to u squared over 2 sigma. So what you end up solving is something like this equation. So this is called the critical inequality. I've written as the inequality. So the if u satisfies this, next time we come back and show that for any u that satisfies this inequality, we get this simple bound. So you get this plus that. So this is the radius that controls the rate. Okay, so the u that solves this would be a direct upper bound on the deviation. And so you're going to try to find the smallest u that satisfies this equation. This gives you the best bound. This part is unavoidable because of the noise. And then the question is that how to calculate this, and then how to solve this, and how to get the rate. And I'm going to come back and do these, and then later on we prove the result. Okay, sounds good. Okay. Thank you guys. See you next time.